Good morning. I am Dr. Raviraj Guru here. Today we will discuss about the heat transfer. The word is heat and transfer. Heat we have to transfer. It may be heat transfer, it may be heat dissipation, it may be heat loss. Now there are three modes of the heat transfer: conduction, convection, and radiation. Now conduction modes of the heat transfer. Conduction of heat through a substance is due to the exchange of energy between the molecules by direct interactions. Conduction occurs in solid, liquid, and gases also. The conduction phenomena is greatly affected or influenced by the flow of free electrons. Now, the Fourier's law of the heat conduction. The relationship between the rate of heat flow and temperature gradient can be derived from the Fourier's law. So basically, conduction, there is Fourier's law. So in convection, there is Newton's law of cooling, and in radiation, there is Stephen-Boltzmann's law. Again, I am repeating. If there is conduction, Fourier's law will be there. If there is convection, Newton's law of cooling will be there. And if there is a radiation, then there will be Stephen-Boltzmann law. So these three laws we have to study here. Step by step we will go. First we will go for conduction, then convection and radiation. Now, Fourier's law of the heat conduction. It states that rate of heat flow or heat transfer by conduction per unit area normal to the direction of the heat flow in any direction directly proportional to the temperature gradient present in that direction. Again, I want to repeat. Fourier's law states that rate of heat flow by conduction per unit area normal to the direction of the heat flow in any direction is directly proportional to the temperature gradient present in that direction. For heat flow in each direction, mathematically, it can be written as Q by A is directly proportional to the dt by dx. Q by A is directly proportional to the dt by dx. Now, Q is directly proportional to the A into dt by dx, or we can write Q equal to minus Ka dt by dx. Now, why minus sign is there? I will explain later on. Q equal to minus Ka dt by dx. Now, Q is a rate of heat flow. Heat per second. So, joule per second or watt. A area normal to the direction of the heat flow in meter square. A area normal to the direction of the heat flow in meter square. dt by dx. Temperature gradient in the direction of the heat flow in degree Celsius per meter. dt by dx, that is temperature gradient in the direction of the heat flow. The unit is degree Celsius per minute per per meter or Kelvin per meter. Here we have to consider only x direction. Then K, constant of proportionality, and it is also called as thermal conductivity of the material. The unit is watt per meter Kelvin. Watt per meter Kelvin. The negative sign in above equation indicates that the heat is always flow in the direction of lower temperature, from the high temperature to low temperature. So temperature gradient in the direction of the heat flow is negative. The negative sign in above equation indicates that the heat always flow in the direction of the lower temperature, that higher temperature to lower temperature. That's why the sign is negative. Sign is negative. You can observe here T1 to T2. So heat is decreasing. That's why in equation Q equal to minus Ka dt by dx. Now here the heat conduction in that figure, heat conduction through a slab or thick wall. Where thick wall, you can see here in that thick wall, the thickness of this wall or slab is B. Temperature, initial temperature or heater is attached here. So we can say this is a temperature T1 which is highest, and T2 gradually temperature decreases in X direction. Consider a wall or slab of surface area A and thickness as shown in figure. T1 temperature at wall 1, T2 temperature at wall 2. According to the Fourier's law of the heat conduction, Q by A equal to minus K dt by dx. So Q dx equal to minus K dt. Integrating between the boundary condition. Now there are boundary condition x equal to 0, t equal to t1, x equal to b, t equal to t2. So In that equation, put the boundary condition. So here 0 to b dx equal to minus ka t1 to t2 dt. So while solving, you can see here you have to integrate this equation considering boundary conditions. So here you will get q into b minus ka t2 minus t1. You have, if you want to remove the minus sign, you take here t1 minus t2. So q equal to ka by b t1 minus t2. So here this equation is very important while solving the numericals. Q equal to ka by b into t1 minus t2. Okay, so here again, what is thermal resistance, what is thermal conductance? Okay, and this is for single slab. If there are two slab, if there are three slab, composite slab are there, then what equation we have to write, we'll see. Now electrical analogy of the heat conduction. You see here, electrical analogy of heat conduction. So here resistance, we can see here R thermal, then here current is flowing, current is here, here heat is flowing, difference is voltage difference is here, and there is a temperature difference. So there is an analogy here, voltage difference in electric circuit, here temperature difference, here current is flowing, here heat is flowing, here resistance is there, electrical resistance, here thermal resistance is there. So analogy we can write here, quantity of heat flows, that is in electrical system, electrons, here heat conduction heat, rate of flow, that is I in ampere, here Q in watts, driving force, here voltage in voltage, and here delta T in degree Celsius or Kelvin, responsible factor, that is resistivity, length of conductor, cross sectional area of conductor, here thermal conductivity and width of the slab. So V equal to IR, standard equation, I equal to V by R, here R equal to rho L upon A, so I equal to V upon rho L upon A. In thermal conductivity equation, Q equal to Ka by B T1 minus T2, so K by B delta T. So again we'll write Q equal to delta T upon B by K, so delta T upon R thermal. So B by K, this is called thermal resistance. So delta T upon B by K or delta T upon R thermal. In electrical analogy, I equal to V upon rho L by A, or we can say R electrical, V upon R electrical. So this is the electrical analogy. Now heat conduction through composite slabs. So in previous equation, we have seen, we have derived the equation for single slab, single wall. Here we have to solve the equation for the composite wall. So here you can see again T1, this temperature at wall, then slab 1 and slab 2, or wall 1 and wall 2, where thermal conductivity of the wall 1 is K1, thermal conductivity of wall 2 is K2, because materials are different, that's why thermal conductivity is different. Then in interfacing between two walls, there is temperature, we can say T2, and after that at the end of second wall the temperature is T3. So rate of heat flow is same, constant. Then thickness of the slab 1 or wall 1 is B1, thickness of the wall 2 is B2. So Q equal to normal formula Ka delta T upon B, Q equal to delta T upon B by Ka delta T upon R. Now thermal resistance for slab 1 and thermal resistance for the slab 2, that is B1 upon K1A, and here B2 upon K2A. So R thermal equal to B1 upon K1A plus B2 upon K2A. Now rate of heat flow is Q equal to delta T upon R thermal. So delta T is from first wall to last wall, first side of the wall and last side of the wall 2 or slab 2. So T1 minus T3 upon R thermal. Now heat conduction through infinitely long cylinder. Now we have seen up to for the slab. Now here we will see the heat conduction through infinitely long cylinder. So in diagram, we have to consider the long hollow cylinder with inner and outer radius as R1 and R2. T1 temperature of the inner surface, we can see here. This is the diagram. So here infinitely long hollow cylinder with inner and outer radius as R1 and R2. T1 temperature of the inner surface, T2 temperature of the outer surface, L length of the cylinder, K thermal conductivity of the cylinder material. So here you can see R1, R2. R1 is the radius of the inner cylinder, R2 radius of the outer cylinder. Then T1 inside temperature, T2 outside temperature. So for integration, consider an elemental ring of thickness dr as a distance r from the center. The surface area of the ring is 2 pi r L. L is the length of the cylinder, hollow cylinder. From Fourier's law of the heat conduction, Q by A equal to minus K dt by dx. So here for cylinder, Q by A minus K dt by dr. Radially heat is flowing, so dr is taken. Then A, this is the surface area, that is 2 pi r L. So Q upon 2 pi r equal to minus K dt by dr. Again I am repeating, this is for the cylinder. So Q by A equal to minus K dt by dr instead of dx. This is r, in it is in radial direction. Then area, surface area, that is 2 pi r L. Okay, 2 pi r is the perimeter into length of the hollow cylinder L. So Q upon 2 pi RL equal to minus K dt by dr. So integrating between the boundary condition, R equal to R1, T equal to T1, R equal to R2, T equal to T2. Again we can see R, when R equal to R1, for this surface temperature is T2. When R equal to R2, for this surface the temperature is T2. So integrating R1 to R2 dr upon dr upon R equal to minus K T1 to T2 dt. Solving this equation, you can see here, you will get the equation Q equal to 2 pi Lk T1 minus T2 log R2 by R1, or Q equal to T1 minus T2 log R2 by R1 2 pi Lk. So we can say Q equal to T1 minus T2 R thermal. Okay. Then heat conduction through hollow sphere. Consider a hollow sphere with inner and outer radii, that is R1 and R2. The temperature of the inner and outer surface are maintained at T1 and T2. Same what we have studied in the hollow cylinder, that same thing we have to study in the hollow sphere, but there the formula for the surface area is different only. There in hollow cylinder the formula is 2 pi RL. Here the surface area of the ring is 4 pi r square. So same formula, Q by A minus K dt by dx, Q by A equal to minus K dt by dr, Q upon 4 pi r square dr minus K by dt. Again same boundary condition, R equal to R1, T equal to T1, R equal to R2, T equal to T2. So same equation we have to integrate. While solving, you will get the formula Q equal to 4 pi K R1 R2 T1 minus T2 upon R2 by R1, or Q equal to T1 minus T2 upon R2 minus R1 upon 4 pi K R2 R1 R2. So equal to Q equal to delta T upon R thermal. So here thermal resistance given, because there are so many numericals where you have to calculate you have to find out the thermal resistance. Then convection, forced convection and natural convection. Newton's law of cooling. It states that the rate of heat transfer is directly proportional to the surface area and the temperature difference between the surface and flowing fluid in the direction of the heat flow. So Newton's law of cooling, that is forced convection, natural. Q equal to, Q is directly proportional A into T minus TF. Now T is the temperature of the surface in 0 degree Celsius or Kelvin. TF temperature of the surrounding fluid, not 0 degree Celsius, in given temperature, that is degree Celsius, and TF is the temperature of the surrounding fluid. So H is the convective heat transfer coefficient. The formula unit is the watt per meter square Kelvin. So Q equal to Ts minus Ts, surface of the hot surface, we can say. From here we have to transfer the heat. So Ts minus Tf upon 1 upon Ha. So delta T upon R thermal. So R thermal equal to 1 by Ha. Overall heat transfer coefficient, that is, it is the term equivalent to the convective heat transfer coefficient, which can be used to find the rate of the heat flow through composite structures. So in next session we will see the overall heat transfer coefficient. Thank you.